thank you everybody for coming, and welcome to this, the third UMAPS colloquium for the current UMAPS cohort. I'm really happy to see that many of our presenters today brought along their lab mates and other colleagues from Michigan, and even brought along audience members from South Africa. So welcome to everybody. We are also live broadcasting this on Zoom. I don't know if there's currently any Zoom attendees, but if there are, welcome to you also. Because we're on Zoom, you know, when we get to the Q&A period, we have microphones, and I'll ask that you use a microphone to ask a question so that any member on Zoom can also hear this. So before we begin with our first presentation, we always have to say thank you, and those of you who have been attending the UMAPS colloquiums would have heard all the many thank yous already, but it's important enough that I think we have to repeat them every time. So thank you to everybody who supports the UMAPS program financially, makes it possible, and that includes the offices of the presidents and the provost for the University of Michigan. They have supported this program since its inception 15 years ago, and I think it's a real statement of faith from the university that the administration has supported this program for so long. They support it, of course, because it is of great value to the University of Michigan, right? So having African thinkers on our campus is really important for our campus community, right? Otherwise, our students would only ever learn about Africa from a textbook. Now they can share a lab bench with somebody from Africa or sit around the conference table, and they can learn that Africa is a place where knowledge is created rather than only about which knowledge is created. So it's really important, and university benefits greatly from the presence of these illustrious scholars in our community. So in addition to saying thank you to the university for supporting the program, also thank you to our UMAP scholars who come and spend 5 months with us here on campus. And as you've heard me say, also thank you to your home departments who released you to come and teach here. Oh, not teach here, not teach while you're here, which means that somebody else has to do your teaching at home. So please also say thank you to your colleagues and your home universities that they are willing to lend you to us so that we get the benefit of your presence here. And also, you know, while we're talking about thanking people back home, not everybody is as fortunate as John to have his spouse with him. So the rest of you, please say thank you also to your families that they have released you for this time to come and spend time with us. In addition to the president and the provost office who have supported the UMAPS program, there's also other individuals and units on campus that have supported us and continue to do so. So we also need to say thank you to them. The Department of Afro-American and African Studies through their South African Initiatives Office has for many years supported the UMAPS program. We also regularly get support from individual faculty members who use grant funding or funding from their research accounts if they want to support a UMAP scholar to work with. And then we're also really fortunate to work with the development office at the University of Michigan. The development here means fundraising. And we have been really fortunate in also raising philanthropic support for the program over the years. So thank you also to our outside donors for the program. I think those are all the thank yous. So next we will then go into the presentations for this afternoon. We have 3 presentations today. They're all in the STEM area and rather technical. We have one more UMAPS colloquium happening 2 weeks from today, same time, same place. And that's also STEM, health, engineering oriented. So if that's where your interests are, come back 2 weeks from today, same time, same place. Our first presenter today, let me get to my notes to make sure I say everything as I should say them. Our first presenter today is Anslyn John. Anslyn comes to us from Stellenbosch University in South Africa, and here at the University of Michigan, he works with Professor August Everhart from Physics Department. Anslyn, over to you.
Thank you, Andres. Good afternoon to all of you, and welcome to the latest in the UMAPS Colloquium series. As you've heard, I'm Anslyn John. I'm an academic based at the Department of Physics at Stellenbosch University in the heart of the Cape Winelands in South Africa. At the University of Michigan, I'm based at the Department of Physics here in Ann Arbor. And today, I'm going to talk to you about cosmological structure formation with shear viscosity. Now, that's a bit of a mouthful, so I'm going to try to unpack this in what is hopefully an accessible manner to everyone here and beyond. So, without further ado, what does one mean by cosmology? So, I have adopted this line as my working definition of cosmology, namely that it is the scientific study of the origin, composition, and development of the universe on large scales. Over here, you see a very nice picture, which is a composite of 3 snapshots of the universe in its infancy. This was taken as a result of 3 different satellite experiments in the 1990s, the early 2000s, and the 2010s by Kobe, WMAP, and Planck. And this represents what the universe looked like when it was only 379,000 years old. So if you are happy with analogies, and I'm afraid I might inflict several of them upon you today, this is like looking at a picture of the universe in its embryonic stage. This is the oldest fossil we have ever found. It is actually impossible to see further back than this time using electromagnetic radiation or light. There are other ways in which we might possibly peer further back, but to date, this is as far back as we can go. And there are at least 3 Nobel Prizes associated with the science behind these images. So this is a very important graphic for those of us in cosmology. Okay, so that's the universe when it was very young. And I'd like to set the stage. When we're talking about the universe, it's important to figure out where exactly we are. So where are we? We're somewhere here on this 3rd rock from the sun, as the old line goes. And this is our solar system. This is its current composition since Pluto was demoted to dwarf planet status in 2006. So this is essentially where we're sitting. Humanity has yet to set foot on any of the other planets. We've barely got to the moon. But if you think of space, you probably think of an image like this, you know, the sun and a bunch of planets and dwarf planets that surround it. If you were to step out a little further, you might discover the Milky Way, which is our galaxy. In fact, the term galaxy does mean Milky Way from the old Greek. And so it's a large collection of lots and lots of stars and gas. The sun is somewhere around here, if memory serves. So we're about 1/3 of the way towards the center of the galaxy. So that's our Milky Way. It's pretty massive, and it's a typical galaxy. It's not the only galaxy in existence. It forms part of what's known as the local group. Now, the local group has our galaxy here, the Andromeda Galaxy, various satellites and dwarf galaxies, and we believe that it has about 80 members or so. Classification is ongoing. The science continues to be updated. But that's our local group of galaxy. This is where we are. And if you were to wait around for a long time, you'd get a lot closer to the Andromeda Galaxy, which happens to be on a collision course with us. So don't hold your breath. This is not going to happen for a very long time. But things are going to get a lot more interesting in the future. OK, so that's the local group of galaxies. The local group forms part of what is known as a cluster. Now, a cluster is a large gravitationally bound group of galaxies. They're basically the largest objects in existence. So this is an image of the Virgo cluster, which, like a typical cluster of galaxies, has thousands of members. Okay, so we're also moving towards the Virgo cluster at a certain speed. But we can go further still, and we have. This is an image generated by the Sloan Digital Sky Survey in the early 2000s. And these points represent lots of clusters very similar to Virgo. So space is enormous. When we talk about the universe, we're referring to things on these sorts of scales. OK, so all the images I've shown you so far have been created or produced in some manner or the other by detecting light or various types of electromagnetic radiation in telescopes. And all of that light and all of that radiation was emitted by objects like stars, which are made out of the sort of chemical elements we're all familiar with, hydrogen and helium and so on. Okay, so this is what cosmologists refer to as baryonic matter. And why the qualifier? The reason is that baryonic matter only makes up a small fraction of the total energy of the universe. So here's a well-known pie chart. So all the stuff we're familiar with, baryonic matter, things like hydrogen, helium, gold, uranium, that all sits in this yellow slice. That only makes up about 4.9% of the total energy of the universe today. Okay? The way we see these galaxies through detection of electromagnetic radiation, so photons of various wavelengths, whether they're visible, infrared, ultraviolet, or X-ray, that makes up an even tiny slice. We're talking about thousandths of a percent. So we can't even represent that very nicely on this diagram. So pretty much almost everything we know of sits in this little tiny slice. Most of the universe's energy is sitting in the form of dark matter and dark energy. Okay, so I'm going to focus on dark matter for this talk. But very briefly, dark energy was something that was discovered in the late 1990s by two teams of astronomers, and that led to a Nobel Prize. The dark energy phenomenon is unexplained, but it does cause the expansion of the universe to accelerate at very late times. So this is a very active area of science, and many people at this university work on the dark energy problem. But I'm going to focus on dark matter. So what is dark matter? Well, dark matter makes up most of the mass in galaxies and clusters. Okay? It doesn't shine or radiate, hence the name dark, and it has a small velocity dispersion, so it will typically be quite cold. Dark matter does interact with the rest of the universe, but only through its gravitational force. Okay, so it doesn't radiate, it doesn't seem to obey the nuclear forces, but it has a lot of gravity. So if you like, dark matter makes up most of the mass of these galaxies. We also know that it cannot be made up of ordinary periodic table matter, like baryonic material. No known particles have the properties of dark matter. And this is quite exciting for our colleagues in particle physics, because new particle physics models are needed. And many candidates have been proposed over the last few decades, and these include things like axions and supersymmetric partners. I'm not going to say too much about the particle physics side of things, but there's a very nice interplay between astronomy and particle physics through phenomena such as dark matter. To date, we have yet to detect dark matter particles directly. We haven't been able to put them under a microscope and dissect them. We have not found any of these new particles in our colliders and detectors. All the evidence we have for their existence comes from indirect astronomical observations. Okay, so I'm going to focus on that. So there are several pieces of astronomical evidence for the existence of dark matter. Probably the most well-known, but not the earliest, is the evidence that arises from the rotation curves of galaxies. So here you see a typical sort of galaxy, and the stars and dust rotate about the center. And you can measure the rotational velocities of these objects as you move further and further away from the center of the galaxy. And the curves that you predict for the velocity distance diagram show up in this red line, and that's from using the masses of all of the stars and dust sitting in the galaxy. That is completely at odds, especially out here, with what we see. So we measure the white curve while we predict the red curve. These two curves can be reconciled if most of the matter in this galaxy is non-luminous or dark. And we've observed this in lots and lots of galaxies. Another piece of evidence for the existence of dark matter is the phenomenon of gravitational lensing. And this is a prediction of Einstein's general theory of relativity, which is the subject I work in. And the basic idea is that a large concentration of matter can distort the space-time around it. So instead of traveling along straight rays, photons feel the change in the geometry of space around these dense concentrations, and they start to travel along these curved rays. And so an observer sitting on Earth looking at a galaxy here through this dense cluster full of dark matter will not just see a single galaxy, he or she will see multiple lensed images of that galaxy. So gravitational lensing is another piece of evidence. Most of the material in these clusters is made of dark matter. Here are some examples of gravitational lenses. This is the so-called twin quasar, which was observed in 1979. So it looks like I've got these two bright images right here. Those are actually the same object. They've been lensed by a galaxy sitting between the observers and the object. So this was the first known example of gravitational lensing, and this really started to convince people that dark matter exists. We can also see these gravitational lenses if you look at the Arbel 2218 cluster, and these galaxies are lensed here, and all of these arcs represent gravitationally lensed images. So gravitational lenses abound in nature. We've seen quite a lot of them since the 1980s. And my next slide has got nothing to do with dark matter, but it has quite a lot to do with gravitational lenses. So I'd like to introduce you all to Sagittarius A star, which is the supermassive black hole that lives at the center of our galaxy. And this image was produced using the science of gravitational lensing, and in fact was announced just a few hours ago by the Event Horizon Telescope. So it's an exciting time to be in astrophysics. So say hello to the big object that lives at the heart of our galaxy. Okay. So that's gravitational lensing. There's another piece of evidence for dark matter's existence, and that comes from the cosmic microwave background radiation. In my first slide, I showed you an image of the universe in its infancy. And so this represents the temperature variations of the sky. So it's done in false color. This is all done in microwave. And so from an image like this of the variations in temperature, one can generate what's called a power spectrum. And I really do not have time to explain how one generates a power spectrum, but there are people in this room who do know how to do this. So you could ask them afterwards. I won't identify you by name. But essentially, that image can be converted into this power spectrum. And if the universe's matter content was purely baryonic, it would be completely inconsistent with the images we see of the cosmic microwave background. So this is yet another piece of evidence that most of the matter in the universe is dark, and there's a hell of a lot of it. Okay, so that's the composition of the universe. Has it always had this structure? Has it always looked the way it does? The answer is no. The universe is a dynamical entity. So this is probably the single most used slide in cosmology talks. This was generated by the UMAPS team back in the early 2000s. So you can look at this from left to right. And so time starts off at the left of this image and proceeds along the right. So about 14 billion years ago, you had the Big Bang singularity. And this takes us into the era of quantum gravity, where we have some very speculative theories of physics that have yet to be firmly established. But as time proceeds, we start to move towards more well-established physics. There's an early phenomenon of inflation, where everything accelerated. The cosmic microwave background radiation was emitted after 375,000 years, when the universe became visible for the first time. Then you have this dark age period before the first stars started to form. And so the universe went from being dominated by radiation to being dominated by matter, and today by dark energy, when things are not just expanding, but expanding at an ever-increasing rate. And during its history, galaxies started to form. So we want to know how the universe evolved from this very smooth, hot, and dense early state to this fairly cool, inhomogeneous, and diffuse system we see today. And that is the central question of structure formation in cosmology. How did this happen? Well, the main idea deals with something called stability. So very simply, stability of a system refers to this sort of configuration. Here I've got two footballs, and those are soccer balls, not American footballs, so they're nice and round. So I can place them on top of a hill and at the bottom of a valley. If I give the red ball a slight nudge, it'll fall away from the top of the hill. That's an unstable configuration, whereas the green ball is quite stable against small kicks. Okay? So when we're studying structure formation, we're interested in the stability of configurations of the universe. Okay, so small kicks or linear perturbations can either be stable or unstable, and linear sorts of problems can either be solved analytically or numerically on laptops, whereas nonlinear perturbations, very large kicks, those are very complicated behavior, and those can be done on large clusters of computers, not clusters of galaxies, and supercomputers. So this becomes quite computationally expensive. The gravitational instability paradigm is how we believe all of the structure formed. And so there's competition between the self-gravity of a fluid and the pressure. So gravity wants to squash everything down to a point, and the pressure wants to push everything outwards. Can the system achieve a stable configuration, and when does it become unstable? So this is known as the Jeans stability criterion, and this is well studied in fluid mechanics and has been successfully applied to cosmology. Now, we can explain the structure of the universe by doing very sophisticated simulations. And if we had to simulate universes just containing baryonic matter, we simply would not be able to reproduce the universe we see today. We really do need a large amount of dark matter in order to be able to produce, to explain the observations we see. And so structure formation provides yet another piece of evidence for the existence of dark matter. This is an image from the Millennium Simulation, which is quite a famous result. And we're fortunate to have one of the authors of that paper in the audience, who is August Everett, sitting over there. And this really represents the state of the art in cosmological simulations. Okay, so we've got a very successful paradigm of explaining how large-scale structure forms, but there are a number of problems. And these problems all show up on the small scales. So this has been called by some people the small-scale crisis in cosmology. Not everyone uses the term. Not everyone agrees that some of these things are problems. But the small-scale crisis, and I've listed some examples here, essentially points to the fact that our simulations and our models produce far too much structure, far too much clustering on the smallest scales. So my proposal of dealing with this it involves viscosity. So a lot of these solutions to the small-scale problems involve baryonic feedback. So on the smaller scales, the baryonic matter becomes important, and this seems to solve many of these issues. People have also tried to do some more radical proposals, like modifying Newtonian dynamics or modifying general relativity. I've focused on on a less extravagant approach, which was to incorporate viscosity in our dark matter models. Now, what do I mean by viscosity? Viscosity is essentially resistance to fluid deformations. Bulk viscosity is a resistance to changes of volume, and shear viscosity is a resistance to a change in shape. Most work in cosmology seems to use bulk viscosity because bulk viscosity can preserve the appearance of spatial homogeneity and isotropy, so no preferred positions and no preferred directions in space. Shear viscosity will violate that, but it can become significant at much later nonlinear stages. So I've been looking at shear viscosity in dark matter. So this is the only set of equations I'll have up. If you know anything about fluid mechanics, you'll recognize the Navier-Stokes equations. Basically, we model the universe as an expanding ball of fluid with pressure, density, and a velocity. And the viscosity terms are these complicated bits sitting over here. And this is a perfectly Newtonian treatment, which is a very good description of the universe in the sort of scales that we're looking at. You could do the full problem using general relativity, but it becomes much more complicated. So I'm going to briefly present some results, some early results, and the outlook before finally concluding. So a few studies of shear viscosity have been done. What I've looked at is how shear viscosity starts to affect the structure formation scenarios. Managed to obtain the dispersion relation, which describes the growth of matter in shear viscous cosmology. And the signs are that the growth of structure is being suppressed on small scales. At the moment, I'm going through this, going through the numerics here in order to quantify the nature of the suppression. Future work is going to involve ways to constrain this model using observations, as well as extensions to nonlinear scales, and ultimately trying to incorporate viscosity in n-body simulations. So this is a very long-term project, but that's essentially where I'm at. And to conclude, I'd like to thank the African Studies Center for support through the UMAPS program, the Department of Physics at the University of Michigan for their hospitality, and August Everard, Dragan Husra, and Otavio Alves for very helpful discussions, which helped me refine this project. Thank you.
Thank you, Anslyn. So we now have time for questions for Anslyn. We have about 10 minutes. I am at a loss for what to ask, but I trust there are people in the audience who can ask intelligent questions. And remember, there's somebody with a microphone, so if you have a question, raise your hand, we'll get a microphone to you.
Hello. Yeah, please, my name is John Doe. Yes, I'm from the University of Cape Coast, Ghana. Please, in just simple language, can you just tell us what you have done in just 2 sentences?
How long can those sentences be?
Just 2 sentences. Tell us what you have done in plain language, please.
Okay. So I've developed a model that describes the growth of structure in the universe. So I've modeled the universe as a fluid, which is a very standard thing to do. But this fluid experiences some form of energy and momentum loss, so dissipation. So it's got viscosity. So I had an image up here. So the fluid on the left is not very viscous. The fluid on the right, something like syrup or honey, it's viscous, it's sticky. So the reason for doing this is that the dark matter seems to be clumping far too much near the center of galaxies. And so if it has some intrinsic stickiness or viscosity, that will act to smear out the clustering on these very small scales. So that's essentially the problem I've been looking at.
Was a bit more than 2 sentences, but we'll give you that. So let me follow up on that, Anslyn. I'm not a physicist. The last time I studied physics was in high school 30 years ago. But solids and fluids are rather different things that are subject to different rules. So how come one can model the universe, which consists of things like, this, as a fluid? Is there a certain level at which fluids and solids are the same?
Okay, so that's a really good question. So fluids and solids are what are known as examples of a continuum. Okay, they're nice continuous distributions. The thing about a block of wood or a piece of steel or some plastic is that you can make statements about its bulk properties. You can talk about its mass, its density, its temperature, and so on. And you can do that without actually appealing to the nature of its fundamental constituents. You don't need to know anything about the atoms that are inside it. So these sorts of macroscopic descriptions are very powerful because they're precisely for that reason. And so modeling objects in the universe like stars and galaxies as fluids is actually incredibly powerful and useful. So you can make statements about the temperature, the densities, and the velocities of these objects without necessarily knowing what they're made of. Ultimately, we want to know what they're made of, but if we can restrict the class of candidates by knowing something about their bulk properties, then you're doing well. So this is a slightly different approach from particle physics, where you essentially have a model for fundamental particle, and you make things out of that. Here, we don't know what the fundamental particle is, but we're hoping to be able to say something about it.
Thank you.
Thank you, Anslyn, for your nice presentation. I just want to quickly ask about you and your students. My name is Usisipho Feleni from the University of South Africa in Johannesburg. So I have a question for you regarding your students. And of course, all the South African universities, they talk about, national innovation systems and sustainable development goals. So which SDG are you referring to? And are you trying to innovate something from these equations that are presented by you in slide 25?
Yes, so the innovation comes with trying to solve some of the biggest unsolved problems we have in science. So that is, if that's part of the national program, then this is what we're doing.
So we have a question over here, and then in the back, and then we'll see if we have time for you, Sevias.
Thank you. So this is a pretty specific question, but I was wondering if there's like a quantifiable metric to determine between bulk and shear viscosities. So like in terms of like a parameter, is there like a numerical value that determines bulk and shear viscosities, like the difference between those two?
Okay, so there isn't a single numerical value. There are two different phenomena that are ways in which a fluid can lose energy and momentum. So
I'm not a physicist. So.
Okay. So if I have a ball of fluid and I somehow expand it and make it bigger, and then I try to compress it, okay, so there's going to be some resistance. Unless it's an ideal fluid, there's going to be some resistance to that particular change of shape. And that's essentially what one means by bulk viscosity, is sort of that sort of friction that manifests along those directions. What shear viscosity involves is resistance to a change of the shape. So if I try to twist something, like if I want to tear a sheet of paper, I have to introduce some sort of shear force. They can't, things don't line up nicely. So with a fluid, if I have, say, a tank of some fluid, and I put a plate on top of it, and I move the top of the plate in a certain direction, I'm going to generate a velocity gradient. So resistance to changes in those velocities are a manifestation of shear viscosity. If the fluid has no viscosity at all, it's just going to go where it's pushed. So they're two slightly different things.
So it sounds like there are a lot more parameters for shear, and therefore it's harder to model. Is that correct?
It's actually, there are actually things that aren't even that well understood in fluid mechanics, which is still quite an open subject. And if you're doing this in relativity, it's even more difficult because we're still not sure how these systems will behave under very high densities and speeds. So it's an active area for research in, for instance, neutron star physics, for example. But yeah, understanding viscosity in any situation is quite a difficult thing to do.
Thank you.
Okay, so let's go to our local anthropologist, Nanocrystals.
Thank you, Anslyn. I'm Nosipo from Wits University. Completely up over my head, 90% of what you said, but I'm interested in naming practices in your field, and particularly by Sagittarius A.
Yes.
For the very scientific reasons that, because it's my star sign, like really deeply scientific. But I'm just curious, how do you establish this name of Sagittarius A? How do they come up with these names? And does it have any kind of implications for how this particular thing, what is it? What is this thing that was just discovered today?
Supermassive black hole.
Supermassive black hole in the center of our Milky Way. Like, the naming practices, do they have anything to do with how this particular phenomena appears or what is understood by it? Because there's always this interesting conversation that takes place, particularly when we had the SKA project in South Africa, and people were trying to think about indigenous knowledge systems and how indigenous communities have thought about what is happening in these bodies, which may or may not be at all in conversation with your field. But I'm just curious about the naming practices and what they mean for you guys. And if you know anything about Sagittarius A being named as such.
Okay, so the reason it's called Sagittarius A star is because that's what it appears in the sky along the direction of the constellation Sagittarius. Now, constellations are not scientific things at all. There's just simply patterns that appear in the sky. It's simply a convenient way to denote its position. There are more technical names for these objects. I had a slide of the quasar, for instance. It was QSO something. Pulsars, when they were discovered in the 1960s, were known as LGM, which stood for Little Green Men, because for a brief period they imagined that they might have been signals from extraterrestrials. And I think that has stuck. Oh, no? No, it didn't. It didn't stick. But anyway, there are all sorts of naming practices, but I mean, the names of these objects are quite secondary. It's really their fundamental nature that we're interested in. We could call it something else. It'll still have exactly the same science. Astronomers on other planets no doubt call them something else.
Sorry, Sevias, the keeper of the time says we're out of time. Okay, thank you, Anslyn. Our next presenter is Dr. Usisipho Feleni from the University of South Africa. And here at Michigan, she's working with Professor Bart Bartlett in chemistry. Usisipho?
I don't know. Is it working now? Okay. Where are my slides? Okay, good afternoon, everyone. My name is Usisipho Feleni from the Institute for Nanotechnology and Water Sustainability at the University of South Africa in Johannesburg. Now, the content of my slides will consist of some brief information about the Institute, the current research activities, as well as the research that I'm carrying out in Prof. Bartlett's lab. Now, the Institute for the Nanotechnology and Water Sustainability consists of two focus areas, which is the water sustainability side and nanotechnology. Now, from these focus areas, they are broken down into thematic areas 5 thematic areas. In this case, we have the applied electrochemistry, membrane, and others. And these thematic areas, they are given a thematic area leader. So I'm currently a thematic area leader for the applied electrochemistry. So this particular thematic area deals with the preparation of various nanomaterials. So in this case, we are talking about nanomaterials that are less than 100 nanometers in diameter. So when we synthesize these nanomaterials, we usually use stabilizing agents. These stabilizing agents, they normally have thiol groups, carboxylic group, and carboxylic group. The reason for using stabilizing agents when we synthesize is because we want to formalize a stability of nanomaterials and also to tune in the sizes of the particles. So in this thematic area, we have sensors and electrocatalysts. So it means that when we synthesize and characterize these materials using various instrumentations for optical properties, morphological properties, and electrochemical properties, we apply them in sensors and electrocatalysts. And another way of applying these materials is to use them in energy material. But because we are a team of 5 staff members, we decided to come up with a thematic area or a theme that combines the expertise from sensor side as well as the energy side. So it means that the materials that are produced from sensors and energy can be used for capacitive desalination. Now this slide is just showing the ongoing projects at INANOS, the list of projects, but their details are going to be introduced in different slides. So as you can see in this slide, we have a photoelectrochemical degradation of organic pollutants in water. So if you are looking at this title, it means that we are combining photochemistry and electrochemistry. And as I've said before, we are talking about nanomaterials. So in this case, we're combining nickel oxide nanoparticle together with manganese oxide nanorod to form a composite. So a composite means that it's a combination of 2 or more materials. So when these are combined, they are used as an electroactive material for sensing as well as the degradation. So it performs in 2 ways, not only for sensing part, but also for the degradation of organic pollutants in water. The second project, it deals with the electrochemical wastewater COVID-19 after sensor. So as I was saying before that we're using a nanocomposite. So we can use various nanocomposites. So in this case, we're using gold nanoparticles and combining these gold nanoparticles together with a polymer. So on top of the polymer, we include a biomolecule. So this particular biomolecule of interest is that it can capture whatever analyte of interest we're working in. So in this case, these aptamers that we are talking about, they are specific for monitoring or capturing the COVID-19 in water. Now, the University of South Africa does not only deal with teaching and learning and research. We also have the strategic plan for 2030, which is aligned with the National Development Plan, aligned with the Sustainable Development Goal, as well as the National Innovation System. So I've asked that question from you. So if we are combining all those expertise, it means that we are looking at the Africa Agenda 2063, which one of the aspirations is about nurturing young researchers. So in this case, if we are to nurture young researcher in Africa, it means that we have to develop STEM, community engagement programs. So in this case, we do have some community engagement programs that we are carrying out at UNISA. And this one is close to my heart because it is done in my hometown. in the village. So this community engagement program has to do with the application of nanotechnology. It means that we are applying this nanotechnology for water, for health, and for energy. So we are teaching learners from grade 8 up to grade 12, and also we incorporate these in terms of their curriculum at school. So another community engagement is the STEM program, so for sub-Saharan Africa. So this program is focusing on mentoring or nurturing young girls from 18 to 25 years old. So what we do with these girls is that we are enforcing the use of nanotechnology and how to develop projects, how to identify the problem in sub-Saharan Africa. So the second part of my talk is based on what I'm doing in Prof. Bartlett's lab. The topic that I'm going to be talking about is photocatalytic oxidation of primary alcohol using titania-graphitic carbonitride nanocomposite. I've explained the meaning of a nanocomposite in the previous slide. So my presentation will start from the introduction up to the conclusion. Now, the reason why we are doing this study is because the formation of the carbon-carbon and carbon-nitrogen bond results in the conversion of organic substrates into valued-added compounds. And when it comes to these reactions, they have enhanced with the help of various nanomaterials that can be used as metal photocatalysts when using visible light sources. Now, in this case, as I've mentioned in the title, that I'm going to be using Titania-graphitic carbonitride because of the various properties that I'm going to be discussing in this case. So if you are looking at the properties of these composite material, is that they are biocompatible. Remember, I've spoken about the use of stabilizing agent. If you are talking about a stabilizing agent, it means that some of the stabilizers, they will bind onto your metal and form a stable composite material. So it's because of the low cost. So we're using very low cost materials as stabilizers. And when we prepare this nanocomposite or any material, it's because we want to obtain high surface area. And they're very non-toxic. So we are specific when we're synthesizing these materials. And they promote electrons to and from the electrode system. Now, when it comes to the design of our electrode, is that we normally use FTO, which is fluorine-doped tin oxide electrode, and we electro spin. So that means that we take our nanocomposite and drop cast it on the glass, spin it, and keep it to dry for some time. When the electrode is dry, we use it for electrochemical activities. But then, because we've spoken about the properties of the nanomaterials, we cannot continue with our application without understanding why or what are the sizes and shapes and the crystallinity of these materials. So it is very important to use various characterization techniques to be able to understand what type of materials do we form, what are the sizes that we have formed from the synthesis of the materials. So in this case, we have done some characterization whereby we were monitoring the morphology. So in this case, we are monitoring the particles on top. So we are seeing that we have A, C, and E. So A, C, and E, meaning that we have titanium oxide, we have graphitic carbonitride, and we have the composite material. So you can see that from here up to the composite material, we have changes in the shapes. So that means that if we have changes in the shapes, it means that we have formed our composite material. And then this is confirmed by monitoring the composition of what we have on top of the morphology. So we can see that we have our titanium oxide here. We can see that we have our graphitic carbonitride here. And if we're talking about composite material, we have the combination of the two, which means that we have produced the composite material. So we further looked at the optical properties, because without understanding the optical properties of our materials, we will not be able to understand the visible light, the sensing or whatever we're trying to convert. So in this case, we looked at the absorbance band of what we have produced, meaning that it is important for us to measure or to understand the individual materials before the combination. So if you are looking at the titanium oxide and the graphitic carbonitride, we are seeing different absorbance range. But then when it's combined, we are seeing some slight shift in terms of the absorbance band because of the combination of the materials. And also because we've spoken about the use of stabilizing agent. So this is just to show that if you are using a stabilizer that has carboxylic group, amino group, or a thiol group, you will be able to see the changes in the structures here. So also because if now you are combining two materials, you'll be able to see also some shifts, decrease or an increase in terms of the structural materials. And also because it is important to monitor the crystallinity or the internal structure of the material. So in this case, we combined the small angle X-ray scattering, because the small angle X-ray scattering will talk about the internal structure, the shape and the size of the material. And if you are combining it with the X-ray diffraction is referring to the crystallinity of the material. So we can see, if you're looking at the peak here, this is the combination, the nanocomposite. I'll just focus on the nanocomposite here. We are seeing a peak here, a sharp peak at around 2 in both cases. And we are seeing some changes in the crystallinity here when they are combined. It means that the nanocomposite we have formed are crystalline in nature. Now we've continued with the electrochemical properties of the materials. And if you remember in my first slide, I was talking about these fantastic properties of the composite and nanomaterials and different things. Now, the reason why we develop nanocomposite is because we want to see some changes in terms of the signatures. So if we are looking at the Titania-graphitic, we are seeing some changes here. But then if we have our composite material, we see a very high signature. It means that the composite material behaves much better as compared to the individual particles. Now we have applied our composite material in terms of the oxidation of ethanol. And we were using different scan rates when we were doing some oxidation. And if you're looking at the figure here and here, you can see that when we were doing some readings, we were focusing on the potential window of -1 to 1. But then now, if we are talking about the oxidation, we increased our potential window, because this is the range whereby the oxidation of ethanol or primary alcohol appears. And if you're looking at these different scan rates, you can see some changes in terms of, the electron transfer. And then when it comes to the other activities that we are doing with Prof. Bartlett, we have applied for research funding, which for STEM Africa Collaborative Faculty Seed Fund, and we are now busy writing a research paper. And because I've spoken about a community engagement program and academic citizenship, we have an intern that is busy writing a review article based on water splitting. In conclusion, I would like to say that the composite we have formed, we have successfully prepared our composite material, and based on the results that we obtained on the different techniques, it means that the composite exhibited excellent features. And we have seen some changes when we were trying to oxidize the primary alcohol, which is the ethanol. And I'd like to acknowledge the African Studies Center for giving me the opportunity to be here. Prof. Bartlett, for opening your door, for your guidance, and for your support in everything that I'm doing. For my lab family, I call them my lab family because we do many activities together. We go for games together, and I would like to thank you for all the support, for being kind, and UMAPS scholars for your support and for the good time. Thank you. Thank you so much.
Thank you, Usisipho. And not only did Usisipho apply for a STEM faculty seat grant together with Professor Bartlett, they were awarded the grant, so their collaboration will continue after the end of the UMAPS program. Okay, over to the audience. Questions for Usisipho? There is 50 in the back.
Hi, my name is Gifty, and I'm with the University of Ghana. Thank you so much for your presentation. I would like to know your nanocomposite. How did you decide that your new material will have to be made out of tin oxide and the other material I've forgotten? What was your reason for putting together those materials?
Okay.
And then, secondly, you showed us the signatures, and then we saw that your composite material had a higher. I'm seeing a higher current.
Yes.
How does it make your new material special? Why is the higher current a property that is desirable?
Thank you so much, Gifty, for that question. So I did not go into details when I was explaining the reasons for combining two materials. So most of the time we are looking at the band gap energy. So titanium has a wider band gap. So in order for us to be able to reduce that band gap is to dope titanium with something else. And because we are looking at sustainability, cheap materials, and we know that carbon materials are very cheap. So that is why we combined titanium, because of the wider band gap, together with the carbon material to reduce the band gap. And we all know that if you're combining two things, they are stronger than one. That is why we are having this high current. I'm not sure if I've answered your question.
Well, Gifty also asked, why is the high current desirable?
It is very important to have high current as compared to the individuality because of the oxidation of the material or whatever we're trying to solve. If we are trying to sense, so we need very high current to be able to detect the analyte of interest. Thank you.
Other questions from the audience?
I'm Jim Pennerhan from chemistry. Thank you, it's very nice. I had a question on this slide. What kind of turnover number do you get on the, so you're oxidizing the ethanol, presumably that's the oxidative peak?
Yes, we are oxidizing ethanol because we want to form aldehydes and other compounds. So we have done some work with Lee yesterday on the gas chromatography to be able to see that we have actually converted the ethanol into aldehydes.
Okay.
So that is the reason for doing the oxidation, is because we want to form aldehydes and other compounds.
And I had another question. I apologize if I missed this, but you mentioned photocatalytic. Is this in the light, or is
this one is not in the light.
What happens?
This is
in the light?
electrocatalysis.
Right.
So we are still to do photocatalysis.
I see. Okay.
But
Thank you.
Sevias, this time you get to ask a question.
Thank you so much, Usisipho, for the great presentation. My question relates to your community engagement work in South Africa. There is a project that specifically, focuses on a girl child. From the projects that you showed us, what informed your decision to focus on or dealing with only girls? Is it because? Okay,
Okay.
that's the question.
Thank you so much. I think I have mentioned before that we're looking at different policies. I've spoken about Africa Agenda 2063. And that Africa Agenda has many aspirations. But then one of the aspirations is that we have to train youth. On that youth, we focus on girls. That is why we are seeing opportunities focusing on women in science, because we are trying to follow that agenda as well as the national, innovation plan. Thank you.
You mentioned that project happens in your home village.
Yes,
Where
I'm
is that
from
in South Africa?
In the Eastern Cape, closer to Queenstown.
Other questions? So let me ask a question that is also coming from a non-chemist. I said I did physics last in high school, I did chemistry last in high school. So in these graphs where you show the various measurements for the two things plus the composite, the composite isn't always perfectly in between the two. It's sometimes closer to the one than to the other.
It
Why?
depends on the ratios, because when we synthesize, we use different ratios. If we are using 1:1, you are expected to see something similar. But then if you are changing the ratio 1:2 or 1:3, one of the material that you introduced will be higher because of the ratio.
We have time for another question.
Hi, this is Delia from Stellenbosch University's chemistry. You said you used electro spinning to make your electrodes.
Yes.
Why?
If you are using an FTO, there are so many ways of drop casting your material. You can use electrode deposition, electro spinning, or drop casting method. So we have found that electro spinning works the best because of the composite that we have, and because we want the composite to be stuck on the electrode surface. So that is why we are using electro spinning than the other, drop casting methods.
I think then we can say thank you very much, Usisipho. Our last presenter for today is Dr. Pierre Mubiayi from University of Witwatersrand in South Africa. And here at Michigan, Pierre works with Professor Roy Clark from physics. Pierre.
Thank you. Thank you very much. I will be talking to you about pathways for improving energy applications with nanocrystals. And thank you for the introduction. I think I don't have to go through it. Technology is needed around the world in order to improve life-related activities. So we have energy and miniaturization that are part of the important topics that are targeted by researchers in order to maintain or improve the product and make sure that we have products that are cost effective and ready available to the communities, and all activities that will be related to such product should be activities that will help preserve the environment. So in the same context, let's look at the energy. And by looking at the energy, we have to look at the context of South Africa. So due to depletion of coal and its associated environmental effect, scientists are looking for other means to generate electricity, specifically in South Africa. And we know that in South Africa, electricity that is generated there, it's mostly dominated by using coal. It's around 85.6% of electricity generated through using coal. And comparing to the global energy, we have only 27% of electricity that can be generated using coal. While talking about this, I have to mention that here in the United States, it's been said officially that the USA has reached around 20% of its total energy that is generated through renewable sources such as solar cells and wind energy. So with South Africa, we have 48,000 megawatts of electricity that is produced through Eskom, because the Eskom is the main supplier. But that electricity is not enough. We have now that phenomenon that we call load shedding in South Africa. Means there's not enough electricity. They have to cut electricity from one area in order to supply a specific area. And after that area is fully supplied for a certain duration of time, then they have to give the electricity to the initial part that were in the dark first time. So because of using coal, there are specific environmental effects, such as greenhouse gas that are generated. And South Africa is the 12th emitter of CO2. And its emission, it's actually half of the total emission of the entire Africa. So there's some concerns about how to use or to generate electricity in South Africa currently. And to kind of palliate or bring solution to such a problem, we're seeking the use of nanotechnology. As Usisipho mentioned in the presentation, nanotechnology utilizes nanomaterials. And here specifically we'll focus on nanocrystals. The reason of nanocrystals is to make sure that we have specific unique properties of those dots-like crystals. And if you can look at the image here, the scale bar there reads 100 nanometer. So those dots that you see over there, they are way less than 20 nanometer. So they have unique properties, and the unique properties is actually what we are seeking, so as the material can be utilized later on for solar cells or for other related applications. So here, for sake of comparison in terms of size, our nanocrystals are around 20 nanometer or less. And if you compare it to COVID virus, let me tell you the story about COVID virus. We've been told that we must wear masks every time because we know that COVID is an airborne disease. So we know that through sneezing, when someone sneezes, there's some droplets that can come from there. Each droplet measures around 5 micrometer. And if you convert it into nanometer, that's 5,000 nanometer. We cannot actually see those droplets because they are very small, okay? But now the nanocrystals, if you compare them to the COVID, they occupy around 5 or 6 times the size of COVID virus. Now on the other side, the COVID virus, in one single droplet, you have a chance to encounter a maximum of 40 COVID viruses, just in a single droplet. And so we can understand why they were insisting that we have to wear masks. But nowadays, because most of people are vaccinated around the world, we have at least lowered down that chance of contamination. I'm not a medical practitioner, by the way. Okay, so let's come back now to nanocrystals. I wanted to show you that the nanocrystals, they are indeed small. Because they are small, they have unique properties. And those unique properties include the structural properties, as Usisipho mentioned about the structure. And they also include optical properties. So we'll mostly focus here on optical properties. And the main parameters that one can seek on the optical properties is the band gap. So with nanocrystals, they have the facility of tuning the band gap of your standard or initial material. And the initial material, we call it bulk material. We call it bulk because it's found like that in the nature, or it can only be processed through physical phenomenon. Physical phenomenon, it's like you have apple, you let it decompose somewhere, it's still apple, but it's just decomposing. Whereas chemical phenomenon, here I'm talking to larger audience, so forgive me, people who are chemists who know better than me, or the other people. But when you're talking about chemical phenomenon now, we have complete transformation of the nature of the initial product to something, the initial ingredient to something that is completely different than what we're having, okay? So with nanocrystals, we have a chance to tune the band gap. We can move from narrow band gap to wider band gap. Now, if you consider a certain range of nanocrystals that are made from one type of bulk material, then you can be able to have properties that can collect as much sunlight from the sunlight spectrum, hence have a higher chance to convert, to have higher efficiency in devices if you can use them in devices such as solar cells. So talking about solar cells, let me take you through the history of solar cells. There is the first generation solar cell, second generation solar cell, and the third generation solar cell. We're not focusing on the previous generations because the current generation is the one that people are dealing with, which is the third generation. The reason of it being in place is because of failure from the previous stages or previous generation. So the third generation seeks to improve the efficiency, whereas they trying to work on the materials using new techniques or various other techniques so as to cut the cost of existing solar cells. Currently, silicon solar cell is still conquering the market, and we have the efficiency of around 25–27%. So when you buy a solar cell panel, you have a higher chance to have it made of silicon. Because of the properties of silicon so far, there's no any other type of material that can beat that. Hence, us as researchers, as scientists, as chemists, we try to come with new type of material that can upbeat whatever that silicon is offering us to us. And also another problem so far, that the limits of the normal silicon, the efficiency, there's no way to surpass the current efficiency using silicon alone. And we know that we need alternative source of energy, hence we have to develop new materials. Okay, so the National Renewable Energy Laboratory here in the United States has developed a third generation solar cell, which is an exciting thing, milestone. The solar cell gave the efficiency of around 47%. And I just told you that the current marketable solar cell is around 25–27%. So this is quite a milestone. The big problem now is that the environmental condition in which you have to apply this type of solar cell is a bit difficult currently, and the cost that involved in order to make this type of solar cell is a bit tricky. Hence, we have to come with new techniques in order to produce something that can either keep this efficiency or go beyond that while reducing the cost of the material. So while we're talking about National Renewable Energy Laboratory here in the United States, I'm proud to announce to you that my current host, Professor Roy Clark, was a part of the development to fabricate this type of solar cell, the milestone. Okay, so actually this multi-junction solar cell, it works based on, as from the name, it works based on coupling many layers of, or many panels of solar cells, and you couple them through what we call junction. And that junction has to play a huge role so as it can collect the efficiency of this solar cell, the efficiency of another one, until you can have everything in one place and reach such average efficiency, which is way above the short-click quasar limit, which is the theoretical limit of a normal one-layer solar cell. So our approach now is to bring in the nanocrystals. As I said in the previous slide, we have various properties or various band gap that can be exhibited with each of those nanocrystals. So we'll want to make sure that we apply those properties. Also, preparing this type of material, it's not a walk in a park. Okay, it's very difficult to make these properties, but we will show to you guys, we'll show you in our result that it's possible, it's doable, and we are going that direction. So we can minimize the amount of layers that should be put in a panel while playing on improving the efficiency from this amount or keeping the same value. So there are various methods that can be used to prepare nanocrystals, among which solvothermal method. Solvothermal method requires higher pressure, and beside that we can use also deposition methods. And with deposition method, you need specific steps that are costly, and beside that you need higher temperature in order to achieve the preparation of nanocrystals with such method. So beside those two methods, there's colloidal approach. Colloidal approach requires relatively simple methods that are less costly, and those methods, they don't require very higher temperature. So the reason of making nanocrystals, nanomaterials, or specifically in my project nanocrystals, is because we want to achieve the structural properties and the surface of those materials that can be utilized later on for various applications. And this is a multidisciplinary approach. That's even the reason why, as a chemist, I joined the University of Michigan in the School of Physics, because this is a multidisciplinary approach. You don't have to be a chemist or a physicist only for you to do nanomaterial. You can do this in conjunction with other people from other disciplines. So the nanomaterials can be part of, can be used for medical purposes or biological purposes. Besides that, we can use those materials to make for other applications such as water treatment, solar cells, and so on. So our main target is to synthesize inorganic perovskites and semiconducting nanocrystals. And with the synthesis, we're targeting the preparation of cesium-based perovskites. And the cesium-based perovskite, here I wanted to show you the structure of perovskite. This is a three-dimensional perovskite. It's sort like this so that one can be able to prepare the crystals and have a good arrangement. And such arrangement will allow the flow of electrons through any layer or any film that one will want to prepare later on. So ideally, you have a cubic structure over there with all the atoms that are constituting the concerned perovskite, but within those atoms, there are some of the atoms that are sharing the bond with other atoms from another cube, making thus the three-dimensional structure. So the materials will then be characterized using various techniques, including TEM, which can be used to get to really visualize the nanocrystals that we synthesize. And thin film can also be prepared then laid together in a specific device, in specific devices to make solar cell devices. So with the experimental part, ideally, we just need to prepare the material through the solution of the precursors or ingredients. We dissolve the ingredient in certain solvents, and we mix everything using a coordinating solvent or mixture of coordinating solvent. By controlling the temperature and the inert condition, one can prepare the nanocrystals. Like among those nanocrystals, we can target copper, indium, gallium sulfide. We can target a compound like cesium, bismuth, silver bromide. And when we have those type of compounds, and after optimizing all the parameters of synthesis, if we are very happy, then we can we can characterize the material. So this is the synthesis setup in the lab at the University of Witwatersrand, and this is the XRD, where you can get the nature of the material that you prepare and the crystalline structure. And here, this is a material characterization center here at University of Michigan. This is North Campus, and the lady who is helping me there is one of the staff member, Nancy, who is helping me collecting the result about the scanning electron microscopy. And after, when we are happy about everything, then we can make devices, and the devices will be made with many layers. And to make it short for everyone here, the main layers of the device are the working electrodes, the absorbing layer, and the counter electrode. Please note here that most of the time, or currently, the most marketable solar cells, they have a specific type of counter electrode, including gold, platinum, silver. So our results, just to make it easy for everyone to follow, because I cannot summarize everything that I'm doing in two sentences. I think it's impossible. So I will just tell you some of the results in short before I can show you practically what we have. So we're targeting the study of the nature of the nanocrystals, just to make sure that we have indeed what we are targeting. And then we determine the properties of those nanocrystals and various parameters such as the temperature, the time, the precursors concentration, and the way of mixing them. We will also determine those parameters. parameters properly. And afterwards, the stability of the nanomaterials or nanocrystal will be determined. And this should lead us to confirm that indeed we have nanocrystals that possess unique properties in comparison to the bulk material. And that will give us room to develop new materials that can be used for improving the performance of existing devices. So specifically here, I wanted to show you the stability of nanocrystals. That here we use a cesium lead iodide. One can ask, why are you using lead? Okay, we use cesium lead iodide as a reference because it has been widely studied. And we know that many of the researchers are reluctant to continue with lead due to the environmental effects besides the stability. So we use it as a reference just to see if we can improve the stability. So we, under normal conventional solvents that are supposed to be used or ligand, we realized that within 1 minute, if we prepare it not in glove box, under normal air condition, we have the stability that is compromised within 1 minute. After synthesis. Whereas when we play on the coordinating solvent or capping agent, if we have a diphenyl phosphinic acid mixed with benzyl ether in a certain concentration, then we can really have materials that can exhibit some stability for a long period of time, which is a good thing anyway for anyone who will want to synthesize this type of material. And also under air, because we don't work in inert condition, if we use the mixture of our set capping agent, you have well-defined and well-arranged nanocrystals. So the stability was also studied by checking the cation exchange. Here specifically we look at two types of nanocrystal. Cesium zinc bromide and cesium tin bromide. When you look at cesium zinc bromide, it has very good stability, but all the other properties are not really very good. And when you look at cesium tin bromide, it has very good properties, but when it comes to stability, that like it's not really performing properly. So we had to get a synergistic effect between the two nanocrystals by playing on the concentration of zinc and tin and mix them together. So when we play on the concentration after optimization, we could really get cesium zinc tin bromide with properties that are between the two compounds, and also the nature of the compound that we get. It was really stable, and the stability could be seen after days of keeping the sample under normal conditions. So some of the additives could also be used in order to improve the properties of prepared nanocrystals or perovskite in this specific case. So cesium bismuth bromide, for example, had its limited stability. But by choosing to add some additives, like in this specific case, we chose silver. Silver was chosen because of its excellent optical properties. So we use small amount of silver as additive. When you add them, then you see that the optical properties are really very good. And indeed, the amounts were very small. If you take 0.2, you even half that amount, you still have very good properties. Furthermore, with higher concentration in this specific case, 0.2 millimole, you could see that there's some agglomeration. And agglomeration means that we might not be able to proceed further with our characterization. Hence, we focus on the smaller concentration. We made the film with the smaller concentration, and one could see that there are some big crystals. But if you look into details with these advanced microscopic techniques, you can see that this is one of the big crystals. And if you look into detail, you see that it's made of small nanocrystals that are put together in a certain way to form that big crystal. And so if you expose now those crystals to certain disturbance, and in this specific case, we expose the nanocrystal to higher electron beam. The higher electron beam normally should degrade or damage the material within few seconds. But in our specific case, because the material were very stable, they could resist until 1 minute, 5 minutes, 10 minutes. But at 20 minutes, we could now see that there was some degradation that could be observed, because we could see the small atoms of silver being shown all over the image, confirming that indeed there's a degradation of the mixture that we form, which is cesium silver bismuth bromide. So I will finish in 1 minute. So we went on checking now the electrical performance of the device. So here one can see that with choosing cesium zinc bromide as a junction, remember the configuration of solar cell that I showed in the previous slide. When you use cesium zinc bromide as a junction, you have the Schottky behavior that could be manifested, clearly indicating that we can use this type of material in the preparation of solar cells, especially if one want to play on the National Renewable Energy Lab, which is our reference now as in order to improve on what is existing there. So we went on also checking what is happening at the Cantor electrodes. And I said in the previous slide that Cantor electrodes are mostly made with, they are mostly made of expensive material or expensive metals such as gold, such as platinum, and so on. So we replace gold, platinum, and silver by cheaper material. Carbon-containing materials, they're always cheaper because they're everywhere and easy to get. So we replaced them and we coupled them with the nanocrystals. And the specific nanocrystals that was used here, it was cesium tin zinc bromide. And when we group the nanocrystals with the carbon-containing material, which is reduced graphene oxide, we make nanocomposites. I think I'm joining Usisipho. She made the nanocomposites. I'm making my own for a specific reason. So we use the nanocomposite as Cantor electrodes, and the properties could really show rectifying parameters, and as one could see it from Nyquist board plot, and the S-like shape confirmed indeed that there is reduction of the electrolytes because we use dye-synthesized solar cell as a device. And such properties could indicate indeed that one can use the nanocrystals as Cantor electrodes. We went on making the full device now with our absorbing material as nanocrystals. What we got there is that we could collect good electrical parameters besides the efficiency, which is it's a bad thing. So beside the efficiency. But it's not a bad thing because it's a way forward. You have to move step by step. As I said, it's not a walk in a park. You have to move step by step until you get to something bigger. So the efficiency is here at 3%. And remember what I said earlier, that they got 47%, which is really nothing. It's the reason why it's nothing is because we didn't optimize the condition in which we prepared the device. And also our setup, how do you call it again? Our solar simulator setup that collects electrical parameters was not really well calibrated. As I'm talking to the larger audience, I know that there are people who are experts. We need some help on our solar simulator because the connectors or the electrodes, they're not really holding our sample properly to get what we need. And we also need to play on the detection limits. So in conclusion, we showed that all the three major components of solar cells can be targeted with our nanocrystals so as to improve the properties, and that can lead to the improvement of a solar cell performance. The nanocrystal can be prepared through any method that one can name, as long as you prove that it's the correct method. But our method is really correct, colloidal method, because it's cheap, and all the steps that we use, they really don't require sophisticated apparatus. So you can prepare using any method in order to improve the properties of existing tools. And there are several techniques that are found here at the University of Michigan. We are developing further characterization, and we've done some of the characterization, and I know that the nanocrystal can fully be characterized using the techniques that are found here at the University of Michigan. And we also established collaborative projects with a few people in the School of Physics. Obviously, my hosts, we always interact. When Roy is around, I know that he's around. I have to go to him and we kind of digest everything about science every time. So there's Prof. Agate Ball, with whom we've discussed the atomic layer deposition techniques and the implication of nanocrystals. There's also some collaboration in chemistry. There are many chemists here, I could see. And I've established some collaboration with Stephen Maldonado, and we have to discuss what is the implication of the nanocrystals on the electrodeposition. I've also discussed with Prof. Bart Batley, who is here, about the electrocatalysis and the implication of my nanocrystals that I prepared. There are also collaborations that I've established because I was at the conference here in another city. I've established collaboration with other departments and institutions here in the United States. So I would like to thank, I'm sorry that I passed your time. I would like to thank the African Studies Center for giving me the opportunity to be part of the UMAP program. And it was really good to land here, to get here in Ann Arbor, actually to land in USA and get stuck at the airport. It was a really good experience. And we didn't get stuck at the airport because they wanted us to stay there at the airport. It's because there was a problem in Ann Arbor. And the airport that we used to land in USA, it was not in Ann Arbor. So it was a good experience. And the moment we arrived here in Ann Arbor, it was not really a welcoming moment, but it was a good experience. So thank you very much to my UMAP fellows and for your support and for understanding each other. And I also want to thank the University of Witwatersrand in South Africa and the funding institutions. I also have to thank again my hosts for being patient and support me throughout. We've discussed everything, as I said, and we've even talked many times about life, which is a good thing. I also thank my students, and among those students, there's Olusola Nkibami, who graduated last year on for his MSc. Olusola is currently here in the United States and is doing his PhD at the University of Colorado. And this is a brilliant student because he got a distinction for his MSc. And I would also want to thank the lab coordinator, Professor Nosipho Moloto. Nosipho is coordinating a huge group, and I'm part of that group. We are 6 principal investigators in that group, NanoWebs. We call it NanoWebs, and that's the meaning of the group. So thank you very much to everyone here for their attention, and I also want to thank those who are following us online. I'm not sure if my wife is sleeping or if she can hear me as I'm talking. So if she can hear me, I just have to tell her that this is what I'm up to. Thank you very much. Okay.
Thank you, Pierre. Yes, our current UMAPS cohort had quite the arrival in the US. Right? First, they were delayed by a month because the US didn't allow travel from Southern Africa for reasons that I think all of us agree was not really that well motivated. And then when they arrived, it was in the middle of a snowstorm. Yeah. So they arrived on the East Coast and were stuck there for 3 days before they could finally travel to Detroit. And yeah, when they arrived, there was snow everywhere and it was difficult to get around. But they persevered and they're all here, so thank you. Thanks. Okay, questions for Pierre?
Sevias.
Okay, Sevias and then over here.
Thank you so much, Pierre, for a wonderful presentation. I enjoyed every moment of it. My question is from a non-specialist, position, but you discussed. There's something that touched me, which you actually presented, which is that of South Africa being, I think, the highest emitter of carbon
12, yes, yeah.
in Africa. But of course, I think it's way below, other developed countries.
Yes, yes.
The main reason why you're actually doing that research. And it's important because if we look at the United Nations Development Program, they actually have what they now call the Planetary Pressures Adjusted Human Development Index. And that one is actually focusing on how best we can actually calculate our human development index in such a way that our planet is also reserved intergenerationally, okay, in order to preserve it for the future generation. So with your research and all those things that you are doing, particularly, you know, with respect to contributing to the safe energy, how much of it is actually seeing light in the African context? In other words, how much of your research is being applied in real life? Thank you.
Okay, thank you very much for your information about many things, and thank you for the question. As I said, we're preparing nanocrystals. We're preparing nanomaterials. And those are new materials that bring new properties. And those properties, as I showed with that circle, can be actually applied anywhere, not just solar cells. But when you talk in the context of solar cells, as I said, we are just few steps in the right direction. It doesn't mean that we're already coming with solutions. I cannot come and gloat here that we have conquered what the National Renewable Energy Lab has said. No, we are still far away from there. So we don't have things that are really live to say that this is what is happening now. Like now in our societies, this is what we can say. I cannot say that. But when it comes to other applications, as I showed in that sphere, I have students who were working on nanocrystals, and they applied them for photocatalytic applications, and they use them for water treatment. So it's more or less encompassing what Usisipho presented. So when it comes to the application of the nanocrystals, it happens. But when it comes to solar cells, we are far away from reaching where we want to reach. But I know that with collaboration with the help of other scientists in the world, obviously we'll get somewhere. Thank you.
We have questions over here, and then to Diana.
So I noticed on one of your earlier slides that you showed that with your nanocrystal development, you were actually widening the band gap. Why are you widening the band gap when typically people would decrease the band gap to allow those energy transformations to occur easier? If you could just comment on that for a second.
Okay, thank you very much for your wonderful question. So it means that you are following me properly. That's great. The solar cell configuration, it has what we call working electrodes. And the current solar cells, they have titania. Usisipho talked about titania somewhere. There's titania, which is part of the working electrode. It's a wide band gap material. So your question is mostly about the absorbing layer. The absorbing layer needs to be to have narrow band gap. As I said, when we have a broad range of nanocrystals, we can target anything that is required for solar cell. We can target wide band gap, narrow band gap. And I gave you the range of nanocrystals and show how they can fit each purpose. Okay, thank you.
Okay, thank you so much, Pierre, for the wonderful presentation. My name is Diana Mbatude from Aga Khan University, Uganda, and I'm a UMAPS scholar. So out of the so many things you said that were very interesting, but kind of outside the scope of my understanding, there is something.
Mentioned COVID, yes, okay.
There is something I picked very critically. It's the efficiency of the, like, the most efficient one is like 47%, and what you're working on is 3%. So I started thinking, is it like David facing Goliath? What is how hopeful are you at if everything is improved to what you think it can, how hopeful are you that you can beat whatever latest and most efficient cell is in the market?
That's a good question. Maybe I can throw that question to the person who contributed to the fabrication of that solar cell that we're talking about. Is currently here. But no, let me give you an answer. Prof. Roy, I think, knows we talked about it. So ideally, we really don't want to say that we want to reach that efficiency. It might even be lower because the current solar cell in the market doesn't have that efficiency. If you have a solar cell in your house, I bet it doesn't necessarily have that efficiency. So we want to do anything possible, even if it's about the solar cells that we currently have in the market. That is something that is more affordable to everyone. Although there are already some of the things that are being done in Germany and in many places, so as a solar cell can be the major contributor of electricity in those specific countries. But there are somehow the reason of using new materials. As I said, third generation solar cell, it's being implemented due to the reason of looking into new type of materials. So we really want to show that the new type of material, they have properties. If there's an expert, as I put the instrument there about the solar simulator, the one that can help to measure, to get the electrical parameters of a device. If there's an expert who knows about my material, then we can link, we can kind of make a collaboration and try to work together and improve on what is happening there. It's not like it's Pierre who's going to do this in one day. I'm proposing what is happening. I can get there. Why not? Tomorrow after tomorrow, if I have a big facility to do that, it can happen that you see my name all over the TV that I've made histories. And that's why we do science. And you know when we do science, when you're collecting results in the lab, it's not to say that tomorrow you have to invent something, but you do things step by step progressively. So that's what I can give as answer at this specific moment.
Thank you.
Thank you, Diana.
So I see that Roy wants to comment on that, and then we'll take one question from Peter, and then we'll be done with questions, but not done with today. So don't leave at the end of Peter's question.
Yeah, I just wanted to add something to your question, and that is that even current materials are extremely useful in areas where there's lots of sunshine, which is very typical in sub-Saharan Africa. Even the current materials are revolutionizing the accessibility of electricity in many areas in that part of the world. Now, on an even larger scale, you have to worry a lot about cost and availability of materials and abundance of those elements that go into those coming from natural sources. So it's a kind of long-range project, but even the current situation is very favorable in large parts of sub-Saharan Africa, and is being implemented even with imperfect technology. And then what Pierre's trying to do is to introduce a new family of materials which shows a lot of promise for the future.
Thank you.
So our last question comes from Peter.
Thanks, Piri, for your good presentation. My name is Peter Oviro. From the University of Johannesburg, UMAPS scholar. You did mention one thing. You talked about atomic layer deposition, ALD, and it's a technology that I've been working on. And one of the things I get to know about this technology is that as good as technology is, it's quite expensive currently. When you look at the precursor, the different things you have to buy. Do you think that would be something good for probably what you're looking at? How it's going to help cost at the end of the day? That's one. And two, have you considered probably sort of those doing all the experiments, probably looking at maybe doing some simulation to help with some of the work to get probably some results? Yeah.
Okay. Thank you, Peter. Yeah, I think I mentioned the deposition twice, if I'm getting your question properly. I mentioned the deposition here to say that there's collaboration with Prof. Agate Ball from Applied Physics. She's doing atomic layer deposition techniques. So I wanted to see the implication of my materials on such technique because I've never used it. So I cannot say more about that. But what I know is that, indeed, I said in the when I was talking about the various methods that could be used for preparation of nanocrystals, the reason why I chose, or the reason why we have the colloidal route set up in our lab, is because we know that over all the other methods is the cheapest option that one can use. So I know that it involves higher temperature and many steps that are quite expensive, actually. So, but practically, I'm not sure if I can say if it's doable or not. But I think with collaboration with Prof. Agit Bol, I will have more answer to your question for that. The other part of the question was? Oh, the simulation, yes. The simulation, I was actually looking forward into that. I was thinking that maybe when I get here, I will get hold of, maybe I should join your group. I will get hold of some people with whom I can collaborate so as to do simulation. It's part of the things that I'm looking at for future work. Yeah, it's helpful, yeah, I agree.
Thank you, Pierre.
Thank you.
So each of our UMAP scholars at the end of their time gets a plaque to acknowledge that they participated in the program and also a certificate to acknowledge that they completed the academic writing workshop. Nosipho, this is the last time that you are with us. Nosipho is going to New York for a couple of weeks to work with a colleague there and then returning to South Africa. So Nosipho, you get your acknowledgement of completion of the UMAPS program earlier than your colleagues. Nosipho. And Chris, do you want to join us because you can give the writing certificate? And that's the end of the official activities for today. I'm sure there's more coffee and snacks around the corner. Thank you, everybody.